Well, hello there, guys. Thank you for coming for this, I think, last class. Unless, of course, you want to continue forever. Now, I hope you have begun working on your final exam. And I think it's easier than the second, but maybe I'm wrong. Is it easier? I think much easier, correct? Or you haven't really looked at it, so you don't know. All right. Be careful, don't procrastinate, because you never know how hard the exam ends up being, correct? Mm-hmm. All right, guys, so here is the exam. So first question. So it actually came about as someone was interested in the probability of some litter of kittens that they had. They had, so the litter was 5 kittens, 3 are Siamese. They look Siamese, in other words, right? So apparently, my understanding is that this trait is recessive, which means you need both father and mother to deliver 1 copy of that gene to create the Siamese trait. If only 1 copy is delivered, then the cat will not look Siamese, but will be a carrier. Yes. So I do not know the actual statistics, but I mean, there was this argument. Some people thought that it's very, very likely that the father is Siamese. Others thought maybe not necessarily. So that is what I thought. So assuming that the Siamese phenotype is 1/3 as frequent as the carrier, as the number of carriers, that means that in the wild you have 3 times as many carriers as Siamese cats, and this is then what we calculate. So this is the probability. I will use S for Siamese father and E for evidence in my notation. Yes, evidence meaning 5 kittens. Now this is not so easy to figure out. It's much easier to know evidence, how likely it is to have 5, so 3 out of 5 kittens Siamese if you have a Siamese father. So you want to reverse it. So what do? You write this as the probability of evidence given the father is Siamese times the probability the father is Siamese divided by probability of evidence given father is Siamese, probability the father is Siamese. Now, such evidence cannot happen if the cat is not carrier and not Siamese. So there are 2 possibilities, right? Either Siamese or carrier, right? Which I can write as the probability of evidence given carrier times the probability of carrier. Now, we know that this probability is 3 times as high as the probability of S. Do you agree? So I can, in essence, erase here. I hope you will not mind if I just erase this. And if I erase this, I'm left with a 3 here. That's where I use the assumption that carriers are 3 times as common. Yes? And now I need to calculate probability of evidence. Probability of evidence given Siamese. So think about it, guys. That is now a binomial distribution, correct? It's a binomial distribution because, well, for each trial, each cat is independently going to either exhibit Siamese trait or not. Now, what happens if the father is Siamese? If the father is Siamese, it means that the mother, in effect, decides whether to give the non-Siamese gene or the Siamese gene. The mother definitely carries a Siamese gene, and a non-Siamese gene, because otherwise it's impossible. Yes. So the probability of success for every 1 liter, in other words, the probability a given kitten is Siamese is what? Given the father is Siamese. Could you tell me, please? Type in the comments. Exactly, Andrew. It is 0.5. So what do we have here? So the numerator here, it is 5 choose 3 times 1/2 to the power of 3 times 1/2 to the power of 2. Those are the failures. You can just write it as 1/2 to the power of 5. And the entire thing divided by 5 choose 3. Again, 1/2 to the power of 5 as the numerator, plus 3 from this 3. And now what is the probability that if the father is a carrier, that a given kitten is Siamese? Could you now write this in my message? Very good, right? So that would be 1/4. You can all see why, right? Because well, now if you have a carrier, the mother has to contribute the right gene and the father. So it's 1/2 times 1/2, and that means 1/4. So thank you. I think was it Barry who said it is 1/4. So this is now 5 choose 3. And then here we have 1/4 to the power of 3 times 3/4. Those are the failures to the power 2. Good. And what does this give us? Now we can, of course, cancel everything we don't need here. We cancel this, we cancel this. And just a little bit of simplification tells you that this probability, let's see, did I say this? That this probability is 0.54. So it tells me that this probability is approximately 0.54. So that means that based on at least my assumption, it is slightly more likely it's a Siamese, but about 50-50. It depends on the population. It's very sensitive, right? If I know that there are many more carriers than Siamese cats, then it's actually more likely that a carrier was the father. Right, so you just need to have accurate cat statistics. Without that, the question cannot be fully answered. Any questions on this one? How many of you got the right answer, you think? No? I thought this one was not a bad question, not hard. Okay. Fine. Let's go to the next. Any questions on this question? Any questions on this problem? All understood? I can go to the next. All right. Okay. Now, for question number 2. Yes, I understand. For question number 2, what's happening here? Okay, guys, so this, you should have recognized it as relating to the birthday problem. It's very similar, right? What happens in the birthday problem, you have a bunch of individuals and each of them randomly picks a birthday. What happens here? The individuals are now phone calls, and the phone calls, instead of birthdays, they pick which there are 1,000 phone calls, and they pick which of the million people they want to have each phone call. Okay, so in problem A, I want the exact probability that and I hope I was clear enough. I think thanks to Nicholas and a few other people, I realized that you say several does not mean more than one. It means apparently more than 2, or something like that, right? Well, in my mind, I don't agree with this definition. I think several means more than 1, and I remain by my stubborn conviction. So what is this probability? So what you have to say, the easiest way, I think, to write the exact probability is to calculate the probability that everyone is unique and then take 1 minus it, you see? Because 1 minus it means that at least one person was called more than once, yes? So I would write it as the exact probability as 1 minus, and then, you can do Kafka protocol, but I mean, once they're in your head, you can kind of speed things up. So what's the situation? So we have how many individuals here? We have out of 1 million, we want to pick different 1,000. So that would be 10 to the power of 6, choose 10 to the power of 3. And because I pick them in order, just because at least in my Kafka protocol, it's in order. First phone call, which individual? Second phone call, which individual? This is not combinations, but permutations, which can be expressed by taking this number and multiplying by 10 cubed factorial. Yes? Do you see my Kafka protocol? I didn't draw it here, but do you imagine what I mean, right? So in my success protocol, I mean, I say 1 minus. My success protocol I use is everyone called was unique. So first phone call picks one individual, second phone call another individual. So how can you express that? That means instead of in this protocol, you can say individuals picked in order, and then the 10 cube factorial is distribute them among phone calls, right? So the actual individuals picked, then label them in order 1, 2, 3, 4, 5, but not, and then a permutation of those numbers that tells you first phone call picked, let's say, which of those individuals, right? And onwards. Make sense? And out of how many total universes? The number of total universes is 10, is basically 10 cubed. So basically each phone call can pick a million. You agree? Each phone call can be any one of million. The next any one of million. So so it is 1 million to the power of 6 multiplied by itself 1,000 times. So that would be 10 to the 6 to the power of 10 cubed. Make sense? And you take 1 minus that, and that's the exact expression. So this number is so huge that your computer will get stuck trying to figure it out if you try it with the computer. But if you were in doubt, you could have actually tried much simpler, much smaller numbers. So just instead of maybe 10 to the 6, maybe try 1,000 people, and maybe you choose 10 or something like that, or or 100 and choose 10, just to make it smaller to see what happens, to see if your intuition is correct. Now, what is a good estimate for this situation? Like in the birthday problem, I can assume that there is a very weak dependence. In other words, what I imagine is I actually have 1,000 phone calls, like 1,000 individuals, and there would be 1,000 choose 2 trials for every comparison of phone call 1, let's say, with phone call 5, right? You compare phone call 1 with phone call 2. Do they match on the same individual or not? Just like the people in a room matching on a birthday. Yes. So what would that be? So that means that the expected number of successes, we need lambda, right? The lambda factor for the approximation to binomial or to similar to the binomial distribution, it would be lambda should equal to 1,000 choose 2, right? 1,000 choose 2. That is how many trials we have. So in other words, once we have 1,000 phone calls, 1,000 choose 2 is like comparing 2 phone calls at a time. Now, the probability that a given comparison, let's say phone call 1 with phone call 2, is a match, is that they have a million options of matching, and altogether there are a million squared possibilities. So it's 1 over 10 to the power of 6. Yes? Are you following me, guys? You all understand? And then this is approximately this is approximately 0.495. So 0.4995. Yeah, you can just estimate this. Okay, so any questions on how I obtain the lambda and what's the meaning of lambda? I am using the Poisson approximation. It's a useful approximation whenever you have a binomial distribution or one that is almost a binomial. So where in this case, you see the two successes are almost independent. It's not likely that phone call 1 and phone call 2 had a match. So it's essentially independent. So yes. 2.5, yeah, I guess I would not bother you for that, obviously, right? Why not, right? It's a ballpark. We don't always care about every single thing. We just what's interesting to me is, of course, that it's like the birthday problem, and that you can use the Poisson distribution. Yes, and then the probability that we have more than one match is 1 minus the probability of 0 matches, which is just 1 minus e to the minus lambda. Yes, and that will be approximately 0.4 or 0.39, I said. So if you said 0.4 or 0.39, like 40% chance that that at least one person was called upon more than once. Yes. Makes sense, guys. So it just really the same exact situation if you review it as the birthday problem. If you understood the birthday problem, then you understand more or less what happens here. All right. Text me if you need more explanation about it. How many of you got this question right? In other words, especially this number. How many of you got 0.39 or 0.4? Nope. Well, I mean, I might give you extra points for being so honest, right? Because I thought, sure, we got it by cheating. Although it's not always useful because some people give you wrong answers. And you guys, and if you suspect you are wrong, you want to always wonder if it's correct analysis or not, you can try. Then this is the exact probability, and this is the approximation. You can try it with small numbers. I purposefully gave large numbers so that it will crash your computer. All right, but if you try smaller numbers, you can actually see what it will be. You can just adjust it to be smaller, and then Good. The 1 minus, well, I mean, sometimes you forget. I mean, I try to, I'm not sure how you think of it, but I tend to not, I tend to grade rather generously. It's hard to say. Usually I see a mistake, I think mistake, I don't like it, but I then give you some throw points. All right, the next question. Well, I thought of this question by having incessant arguments with Germans over the summer, and actually made me understand certain things a bit deeper. Okay, so I'm actually, for this question, I'm very, very curious what you had to say. What did you think, guys? And what arguments did you use? Right, so there are many possible partial credits.
I can go through what I did for this problem.
Say it again, Ryder.
I can tell you my thought process.
I would be very happy to listen.
Okay. So what I did was I took, first of all, I did like multiple things. I got the percentage of the total for each pandemic for accrued death versus the population totals.
So just for me to understand better, did you mean you took the red numbers or the black numbers?
Yeah, I did it with red numbers first. So I did like 165 divided by 43,300.
Okay, very interesting. Good.
And then I did, I weighted how did I do this? I weighted the deaths based on the percent of the population that age group was. And I multiplied the deaths by that to kind of make sure they're all weighted the same. And then I summed those up to get a total number that I used as whichever number was highest there. I think I said that's what my most dangerous epidemic was.
So in your conclusion, did you think which was the most dangerous epidemic?
I still came out with E as the most dangerous.
So you still decided E is the most dangerous epidemic. That's interesting. You did. So let me tell you my analysis. So I'm sure you by now are very well aware what this relates to, and it relates to the actual real numbers like this. I just made them simpler, so that I doctored it so the numbers are nice, and the actual tables would be longer. Right now, several questions, guys. So, what is the point of discussing mortality? Right? What is it that you are trying to capture with it? Any ideas, or what would you say about it? Right, so here we list a number of people that died from maybe from the pandemic, maybe not, but basically in those particular years. What's the point of those numbers? Well, what does it mean? What death rate? What does it do? What do I care about the death rate? What is it supposed to signify? Why is it bad that more people are dying? How dangerous? Okay, how dangerous it is a bit better. But what does it mean? How dangerous it is, right? So, in my understanding, it is if you're an individual and you're moving around in a particular time frame, more deaths might mean that your likelihood of dying is higher. You agree? Your probability of dying is higher. There were kind of multiple tons of arguments I had with certain people, right? But in my mind, certain things became, because of those arguments, a bit clearer, right? So you see, one thing is you look at things, and somebody they quote all the time. Like, for instance, you have lots of articles that say, like you open Yahoo, you say sobering fact, well, 800,000 people dead of COVID or something, right? Something like this, they say. So they name big numbers, but the problem with naming big numbers is, first is, you guys, you do not compare apples and oranges. You never do that, right? Even Dr. Mengele knew to use twins for their studies. You know, what's the idea of using twins? Is that you try to control everything aside from what you are researching. Yes. So you want to compare, ideally, let's say if you compare medicine, you want to compare a person with the medicine against the person himself without the medicine, with the placebo, right? That would be the best comparison. Let's say you take this medicine, and what happens to you? And if you don't take this medicine, what happens to you? But it's not always possible to do that, right? So what's the next best thing is to try to make a comparison between, if you do two different populations, to try to make the two different populations as similar as possible to one another. You agree? Now, how do you make it as similar as possible? So radar, notice the first thing is that you can see populations are not the same. Do you agree? Look in the red numbers. Populations are not the same. So the first mistake that many people make, when especially they compare, let's say, what happens today to the Spanish flu, is that they do not take into account how many people lived back then and how many people live today, right? So let's say you might say that maybe more people died of COVID than of the Spanish flu. I'm not sure if it's true or not, but you understand, right? You can make the statement, but the statement is absolutely meaningless unless you're saying also the same people in some sense, right? The same population, everything else is the same. So the first normalization you want to do is perhaps consider this number 165 divided by 43,300, or 806 divided by 80,600. Yes. Why? Because what it does is it normalizes how many dead per unit of population, right? So you might report it as a ratio, or some people prefer numbers. So they say, let's say maybe this many died per 100 people, or this many died per 1,000 people. That's how they like to report those numbers. Do you agree? Yes. That's one interesting thing. So, but here is the other thing that is very, very ridiculous about what usually happens here. You guys, are you aware of what is Procrustes' bed? Do you know who is Procrustes, if I'm pronouncing his name correctly? Oh, you need to read Greek legend. So Procrustes, you came to him, was this nice, hospitable Greek fellow, ancient Greek fellow, and he would place you on his bed. And if you were too long, he will cut off your extremity so that you fit properly on the bed. But if you were too short, he would stretch you to fit the bed. You understand? So what a lot of people are guilty of is the error of Procrustes. You are not the average. You agree? So here, when you take the population and take the number of dead and divide by the population, you are missing the individual people. You see, you are missing the individual people. And I'm going to try to show you this interesting paradox. You see, so let's see this. I even prepared a slide here. I did it using Excel. I just don't have Excel here, so I copied it. Here is the table of death. Here is the table of population. Yes. What did I do? I mean, the first table, it is different age groups. You see it also in the different age groups. Yes. So this is, let's say, I forgot what the age groups are. What are they? They are here, right? So here they are, right? 0 to 20, right? So those are the age groups. I didn't really include them here for the calculation, but I took this number and divided by this number, and I did it for all of them. And this is what we obtained. You see? Now let's look first of all at that I fixed column C. What do you mean fixed column C? I'm sorry.
In the original, on the test, the number I think was 377, but it actually sums to 333. So when you did
this is just with Excel. Maybe I made a mistake somewhere, right? But this is just Excel. I mean, I just copied it to Word, and this is just computer. I didn't calculate. It's a bit boring to divide this thing by hand. So I just made a computer let's say take this number and divide by this number. Take this number, divide by this number. Yes. Now, why did I do that? Now let's see what's happening here. Do you see here, guys? Do you see that if you just take a number of dead for pandemic Eve divided by the population, you get the worst percentage? Do you agree? You get the worst percentage, but here is that Procrustes paradox, because what you're doing is you're stretching or compressing everyone to that same bed. Do you see, Nicholas, why that holds? In other words, the sheer stupidity of what's happening here is, for instance, I mean, the people are arguing, let's say, is vaccine good or is vaccine bad? Is medicine good or is medicine bad? Well, is medicine against heart disease, is it a good medicine or bad medicine? Well, depends. What do you have? Heart disease? Are you suffering from it, right? But they say, oh, everybody has to take this thing, everybody has to eat those pills, right? Everybody has to take blood thinners, but that makes absolutely no sense. I mean, in any normal context, if you are vulnerable, maybe you should take those pills. If you're not vulnerable, it could be worse for you. And this illustrates what happens if you stretch it. Now, look at those numbers. You see those numbers here, guys? I just made it, I made them artificial, but this is what happens. Now, if you are in the first age group, right? This is your probability of dying in this year. but you can see that it's not the worst probability of dying. You have this year and that year was worse. So in other words, if you're in this age group, you fear pandemic C and pandemic D, I think, or whatever the pandemics were. You more if you are between the ages of 0 and whatever, I forgot what the label. Do you understand? So if I live in this time, it's not as bad for me. I'm not as afraid of this as I would of C or whatever else you have here. Yes. Also here, you see, this is a bit bad, but not the worst. I'm much more afraid of A. Do you see? If I'm in this age group, I'm much more afraid of A. If I'm in this age group, I'm much more afraid of C. If I'm in this age group, I'm much more afraid of C. If I'm in this age group, actually, for this age group, it is, didn't they do more? It appears that for this age, where's the 0.5? Something is strange here. I thought there was a 0.5 somewhere, but regardless, apparently for this age group and for this age group, based on this table, I think there should be a 0.5, but whatever, right? Maybe I miscalculated something or somewhere, I need to check it. 0.5, there is a 0.5. There is no 0, there's 0, 0, 1, 0. There is a mistake here. So I see something, it should not be 0. There should have been 0.5, I think. Either I copied something or yes, here it should also be. You see, I made it, I think. Maybe it's a glitch, but I made one of them 0.5, either this one or this one. You see, to make none of them, maybe I glitched when I copied it. But in the last age group, you can see this pandemic is this, right? So whether or not it's a glitch or not, the idea is you can see what I made, right? The idea is that for no, it was supposed to be that for no age group it's the worst epidemic. By the table I see here, it appears that for one age group it is. But that's the point, is that you do not compare a young man to an old person. You understand? You always compare like with like. That's the main principle in statistics, that you never violate. Always compare as much as possible identical to identical. Interesting? Yes. Hopefully you enjoy this. I like such paradoxes, right? Yes. There are many other things, but that's the essence of this question. I do not know. I hope this is just accident. I don't know why is it 0.1. It should have been something else, so somewhere, maybe here or here. But maybe I made a mistake. I try to make easy numbers for you. Good. If you are interested in actual numbers, they are much more complicated, of course, but they can be found on the German statistics. They keep very good statistics, for instance, right? And you can see populations on years. I'm not sure how accurate is their projections, but they are probably better at keeping such information than anybody else. Germans really are good at bureaucracy. If age group, but Nicholas, you don't choose age group randomly, right? There's no, it's just my assessment, my operational definition of when you ask what is the worst, it's basically in which situation you as individual have the highest risk. You see, for somebody something is the worst, for somebody it's the best, you see. So for each particular age group you restrict. This is called Simpson's paradox. You see that there is compounding. So assuming that this is the worst is a Simpson's paradox, because the average of all those things is just like stretching on Procrustes' bed. It does not reflect your unique conditions at all. And you cannot generalize individuals to make them just abstract. It's not working like this, right? You're either 20 years old, or you're 30 years old, or you're 90 years old, and different factors at those ages are different risk factors, right? So that's how I understand it. So for any particular population, in this case, they are more afraid of another epidemic. They're not all afraid equally of the same epidemic, right? But they are, but epidemic E, supposedly, I mean, maybe I made an error with one age group. This is supposed to be, I think, 0.5, or this is supposed to be 0.5. But you get my trend. You see, I permuted those numbers. But the idea is that no population is supposed to is most afraid of this epidemic. It's more afraid of some other prior epidemic. So based on this information, at least, it's still not, obviously not, figuring anything in statistically is very, very difficult, even based on that. But if based on this information, this village researcher is incorrect in concluding that epidemic E is the deadliest of all those available. Yes, and that's when I remove the oldest and youngest groups, epidemic, it was the worst. But how is it worst? I mean, you can see here is 0.5. So I mean, there is only in this table you can see here, right? What's the highest probability of death, right? Here, if I'm in this age group, I'm afraid of this most, right? Not of this. This is my worst. If I look at this age group, well, I'm afraid of this disease most. If I look at this age group, I'm afraid of this most. If I look at this age group, I'm afraid of this most. Here, I might have made a mistake. They're not supposed to be 2 copies of 0.1. But the idea was that there would be a 0.5 and you would be afraid of something else. Here, there is a 0.5 and you're afraid of something else. You understand? So I mean, I might have either glitched or incorrectly copied something. Average mortality for. I'm sorry, Nicholas. Could you elaborate? What do you mean? What is average for mortality for oldest age group? It's a much more open question, as many things are open, right? What is it that you mean? There are many comparisons, but I mean, forget about what anyone tells you, and just at least you see my definition of scary or deadly or no. There are many other definitions of this. That's why it's an open question, right? Is that which, in this particular case, which from my age group, for me, what poses the greatest threat? And if not a single person they feel this greatest threat in E, that means E is not the deadliest. And you, of course, say you can have endless arguments, as I did, of course, with plenty of those Germans that cannot be convinced by anything. Right, because they go in circles. There is basically the circle that because there is a sort of non-comparison to something, right? Something that to me is clear, but very difficult to rigorously and mathematically prove. All right. Any questions on this problem? Any other questions, guys? No? All right. So you understood my, if you wrote something else, I will look at it, right? It's much more open question than other things, but then of course, ask yourself, what does this abstract number mean to you, right? What are you averaging? What do you compare with what? So my understanding is for each population, of course, you see, many of them are gathering together. So for instance, you might say, epidemic E is a bigger strain on hospitals, but I don't know what that means, you know. Bigger strain on hospitals. In other words, you have more hospitals are crowded. But and you can ask, of course, if they did not die in this year or in this time period, has it affected morbidity? Or you can just, you know, you can have. It's like the castle. You cannot ever answer things like this ever, you know, or convince anybody, you know. Usually, you know. All right. So next, This one is easy, correct? Question number 4 is question number 4. So here is how we can solve it. So we have 3 cards are randomly chosen without replacement from an ordinary deck of 52 cards. Given that all of the chosen cards are aces, what's the probability that an ace of spades is among these 3 cards? So the simplest way to think about it is there is no preference for the collection of aces, right? So I can look at which cards are available. So maybe ace of spades is card number 1. So I have this universe. 1, 2, 3 are in, 4 is out. I have the universe 1, 2, 4 in, 3 out. I have the universe 1, 3, 4, and 2 out, or 2, 3, 4, and 1 out. Yes, and in this situation, you can see that here you have ace of spades, here you have ace of spades, here you have ace of spades, and the answer is 3/4. It's always good to do the question in, if you're ever worried that your answer is incorrect, do it in several ways. I kind of feel the question is so easy, you don't need another way, but you can use conditional probability and figure it like this. Do you want me to explain conditional probability with it, or you're good with this explanation? You can right away just look at this question and say 3/4, and that's it, and not be bothered. So you want to see the other explanation? Yes. Why not understand this one? Okay, let me see. Barry or whoever. So what are we doing? We are in the business of considering possible universes, right? Definitely when all the universes are equally likely. Yes. So first for this one, I mean, how many universes are possible? We know that we have 3. We know we have 3 aces. We've selected 3 cards at randomly, and we know we have 3 aces. The question is, what's the probability that the ace of spades, which I label as 1, is among them? So if I have 3 aces out of the 4, they're exactly 4 universes, right? Those universes are designated by the card that is out. So there is universe, well, I designated universe 4, that means card 4 is out. Universe 3, card 3 is out. Universe 2, card 2 is out, and universe 1, where card 1 is out. So there are 4 universes, each of them equally likely. 3 of those universes correspond to your possession of to you possessing the ace of spades, number 1. Yes, which I circled. Is it better at all? So that's how I know 3 out of 4. There are 3 universes that have the property of me possessing the ace of spades out of 4 possible universes given this scenario. Good. That's conditional. Now I was asked to do this question in yet one more way. So that's the slower way, but also works. It's good if you're worried and you want to be convinced that you are correct. So this means a probability that I have, I will call ace of spades by S if you don't mind. And given that I have all 3 aces, okay? So what is that? This is the probability that I have ace of spades and all 3 aces, right? And divided by the probability that I have all 3 aces. Now, what is that? Numerator, it means that I have to select, ace of spades is selected, and I need additional 2 aces, yes? So what's the numerator? Numerator is possibilities are 3 choose 2, which means ace of spades is already in the collection. You see, I'm not drawing the Kafka protocol, but I have a document in my brain. I hope you have one as well, right? So what is the 3 choose 2? It means I have ace of spades. I need to adjoin 2 additional cards from the remaining 3 aces, right? And this is 3 choose 2 divided by 52. In general, 52 choose 3. That's how many possibilities there are to choose 3 cards in general. So there are 52 choose 3 universes divided by probability that I have all 3 aces. It's 4 choose 3. Out of 4 aces, I need to choose 3 divided by 52 choose 3. And what I do now is erase this. Yes, and I am left with 3 choose 2 divided by 4 choose 3, which is 3 out of 4 as before. Good. Of course, my previous explanation is the better one because it's much faster. You right away see it. Right? If you just figure out, you train your head to see what is it we're doing. We're just counting possible universes. Definitely, whenever those universes are equally likely. If some universes are more likely than others, I imagine having identical copies of those universes. So I always imagine counting universes. Good. Wonderful. Now we are by question 5, which I hope was not particularly difficult. Yes. So how do you do question 5? So for question 5, it's a Poisson random variable, and ln3 is the expected value, which means lambda is equal to ln3, if you remember, right? The parameter is the expected value. So what do we get? We get that the expected value is just e to the minus ln3 summation n0 to infinity. Here we have cosine of pi n multiplied by ln3 to the power of n divided by n factorial. I just factored e to the minus 3. So that's the probability mass function, and this is the variable. You can calculate expected value by just applying the function to each individual outcome. And what do we get? Cosine of pi n is just minus 1 to the n, correct? So what is this? This is e to the minus ln3 summation n equals 0 to infinity minus 1 to the n ln3 to the power of n divided by n factorial. Now you recognize this as exponential itself, right? So what is this? This is now e to the minus ln3 times e to the minus ln3, which becomes e to the ln of 1 over 9. And the answer is 1 over 9. Yes? How many of you got this answer correct? Or more or less correct? It's the exponential thingy. Okay, good, wonderful. All right, any questions about this? Just series, it's a bit boring. All right, this one is very annoying, but this is the type of questions that you get on the actuarial exam. That's from the actuarial exam, actually. When you need what more on the exam? You mean actuarial questions? I thought my poor deprived actuarial students. Well, nothing is simple and straightforward, guys. You should no, not in my universe. All right, so this is just very annoying. I'll tell you how I solved it. I actually hate questions of that type, but you know, they ask it on the actuarial exam. Exactly, right? They just torture you. I mean, what I would do if a medical person gave me this question, I just would say, just stop bothering me, just do the analysis and just tell me the numbers, right? So what the hell you want from me? But given this information, we can still work through it. Okay, it's kind of good for practicing the conditional probability stuff. Okay. So 1 second. All right, ready? So what do we want to? So we imagine labeling it, right? So I would label with R what is it? So I need, so I have regular is R and L is low. Okay, so I want to figure out. I'll need a lot of room here, so I need to figure out probability of L. It's okay. You have always a safety net with me, you know. So PRL is what? So that you understand, I don't need to write the symbols. Yes, guys, R is regular, L is low. And then I just begin looking at this garbage. So what do I know? I know how many have low blood pressure. So I have irregular heartbeat and high blood pressure, right? So irregular is R complement. So I see a problem 4, and then I can write it as probability L minus probability R complement L. You see that's more useful to me because I have R complement. I'm already in the realm of irregular heartbeat, and high blood pressure is not quite low blood pressure, but it's already kind of, I bring it to the form in to this Roman numeral 4. Yes, and here I just to myself I take notes. Okay, what is this thing? This thing is 0.22. Yes, and then what can I do with this thing, with R complement L? So what I can do is I can figure out of those with irregular heartbeat. So I want to condition on R complement. So this is probability L minus probability L given R complement, probability R complement. You agree? I use the conditional. So this I know is already 0.22. What about probability R complement? Probability of R complement, I know it here from 3, it's 0.15. Agreed? At 0.15. And I can calculate low given R complement. How do I do that? Well, low given R complement is the next task. That's 1 minus probability high given R complement minus probability of normal given R complement. You agree? So if I don't have high, and I mean I don't have a regular heartbeat or whatever this thing is. If I'm not in the high blood pressure and normal blood pressure, I'm in the low blood pressure. Now this I know something about. So this I know is 1/3, right? Of those with irregular heartbeat, 1/3 have high blood pressure. What does it mean? It's this part. It means that this number is 1/3. Yes. So I can figure out this number. Now, how do I figure out this one? Of those with normal blood pressure, 1/8 have irregular heartbeat. So I need to reverse this again, unfortunately, right? So then you have probability of N R complement. This is the same as probability R complement given N times the probability of N divided by probability R complement. Yes. Now we know the numbers here. So what is this number? This number is 1/8. Correct? That's based on of those with normal pressure, 1/8 have irregular heartbeat. So that's irregular heartbeat, normal pressure. How many have normal? Yeah, so normal is also annoying, but let's first look for a moment at our complement. Our complement is this 15, right? So this is 15. And then normal, I can obtain, I know, what do I know? I know how many have high and how many have low, right? So it's 1 minus the high minus the low. Yes. And now you can see we can now put, we have every information. We know this number, here it is. Therefore, we know this number. And if we know this number, we know everything together, right? You now just bring it all together. 64. What's 64? So if we bring all of it together, where do we get there? Right? So I think if we bring all of it together, oh, I wonder if I will. Well, you know, I mean, you can calculate. So this number here is altogether. This here is 8 divided by 15. This is 8 over 15, and you just patch it all into one thing. I think that means that the answer for the entire thing is 0.2. You say you need to, it's a very annoying question, I know, but what is P end? Probability of okay. I see. All right, good. Makes sense, guys. Just annoying, but involves those are the questions you have to train for the actual exam. This is just one of them, right? You have to answer, I think, 30 questions in 3 hours, 10 questions per hour. Make sense? This is the answer is 0.2 by just putting it all together. Just annoying. Just you do lots of conditional probabilities. All right, so now we are at question 7. What's the answer to question 7, please? Very good. So the answer is 1/3. You would not mind if I skip it, right? I just say 1/3 and we go on, right? Or you do. So why is it 1/3? It's because we have several possibilities. We have the universe yellow, and so the first ball is yellow, the other one is not yellow, or we have not yellow, or we have yellow. So only one has, basically we only know that at least one is yellow. So there is only one universe of the possible 3. And each of them are equally likely. So the answer is 1/3. Now, question number 8, were you successful in it? So how do you do question number 8? It is applying the weak law of large numbers. Why central limit theorem? Weak law of large numbers. You can use a central limit theorem, I suppose, as well, but that's possible. Yes, it is the same number I got, Stephen. Right. So how do you do that? I mean, how did I think of doing it? So I have a fair coin, and what I want is this probability. I want the probability that, let's say I run the experiment n times. So that means I have first outcome plus all the way to the last outcome divided by n minus 1/6. This is the experimental average, and this is the theoretical average I should get. And I want the probability that this is deviating by more than 1% is less than 100, right? So what do you do? So what you do is you take the variance, right? So what do? You just take the variance of this random variable. What is the variance? So the variance of expected value of any xk. Expected value of any xk is 1/6. Do you agree? Because you either get it, we only care for the number 6. Either it's 1/6 where you are successful, as opposed to 5/6 where you fail. And the variance of xk is 1/6. It's this number squared. 1/6 minus 1/6 squared, which is 5 over 36, right? It's 5/36. So because they are independent throws, variance of the sum is a sum of variances, right? So what is the variance? What is the variance of x1 all the way to xn over n? That would be 1/n squared multiplied by n times 5/36, right? Which is the same as 5/36n. And this number, I take this number and when I divide it by 0.01 squared, just check again, just how we just review the proof of the law of large numbers. So I have 5/36n divided by 0.01 squared. This I want to be less than 0.01. So that means that 5/36n should be less than 0.01 squared. And that if you just calculate for n, that means that n should be 13889. If I have this n, if I throw the die this many times, why is that 0.1? Because 99% certainty, right? So that means that that only in 1 out of 100 trials will I calculate the average deviating by more than 1%. You see? So that tells you the rate of convergence. You see, that means that if you run this experiment, you always are going to get unpredictable results, but they are going to be 99% of 99 out of 100 experiments, 99 of them what you want to produce. If this is the n, you would produce a deviation from 1/6 that is no more than 1% deviation, right? No more than 0.01. So not 1%, but 0.01 deviation, right? 1 unit deviation. Make sense? And what did I use? I used the weak law of large numbers. Why did you use greater than 0. Well, over here, because this means that here it means deviation. They mean different things, right? So let's not confuse. This number is the estimate of the probability. That's how low I want the probability. Whereas this number, it means the deviation by how many digits you see. So this is the theoretical average. It's not going to be exactly 1/6. So it might be different from 1/6. So this means that it's farther than 1/6 plus 0.01 or below 1/6 minus 0.01. So this is the width of the interval. I see, and I want the probability that I get an approximation to 1/6 outside of this interval to be small. That's the estimate of how small I want this probability. Good. So I'm estimating the probability that the error is greater than 0.01. Okay, so let's clear this. All right, this one, if you look into my notes, I solved a similar question. Right, so more to coil this. So we're going to construct a sentence of n units in length. Right, a sentence of n units in length and words in length, and in the sentence we want to see how often is to be or not to be occurring. Right, so the way I think of it is I imagine xk to just measure in the word, to just begin measuring at k plus 1. How long this word? 1, 2, 3, 4, 5, 6, right? All the way to k plus 5. And it will, in xk will just look at that segment and tell me, do I see the word there or not? So it will be 1 if the word is there and 0 otherwise. So what's the expected value of xk? The expected value of xk is clearly 1/9 to the power of 6. You agree? Because I have to, this word has to be 2 and this word has to be b and onwards, right? So the probability that this word is 2 is 1 out of the 9 available words. And the next is independently 1 of the 9 available words. So altogether for xk to reach to be or not to be, the probability is 1/9 to the 6th power. Right now, how many xk's do I consider? I consider reading it from the very first point, then from the second point, and from the third, all the way to n minus 6 plus 1. So there is going to be n minus 5 variables. Makes sense? Why n minus 5? The n minus 5, x sub n minus 5 is the last variable, which means that the answer to this question is n minus 5 divided by 9 to the 6. That's the number you expect of seeing this word. So n has to be pretty large for you to, obviously n has to be more than, well, at least it has to be at least 6 units in length. But, you know, you can see that, you know, it has to be pretty large for this to be an average even one word. Right, n minus 5 has to be equal to 9 to the 6 for on average for it to be once. So it has to be a very long string. Make sense? Yes, Nicholas, I did expected value. Probabilities are not independent. It's not easy to say probability, but expected value, it never matters. You know, expected value of a sum of random variables is always the sum of the expected values. It's not so about variance, but always so about expected values. If you look at the proof, you just prove it for yourself. It's always so. Expected value is always linear. It doesn't matter if the variable is dependent or not. They can be strongly dependent as possible. It still is true. So okay, sure. What I'm saying is the expected value x1 plus x2 plus x3 and onwards, right? I don't need to know anything about them. I know it is expected value of x1 plus expected value of x2 and so on. It's always true. I don't need to know anything about those variables being dependent or independent. It's always true. Yes. So review those things, guys. One of the ideas I hope you learned from this class is that expected value of a sum is always the sum of expected values. What do you mean n minus 5 not impossible, Nicholas? Not following? N minus 5 divided by 9 to the power 5. So the answer to this question is, once again, the answer to this question is n is the number of words you have minus 5 divided by 9 to the 6. So for instance, if n minus 5 is equal to 9 to the power of 6, right? So in other words, when n is equal to 9 to the 6 plus 5, you will on average see that sentence once, on average. Make sense? What this means. Good. Next question is the squirrel, and you can solve the squirrel question. You can, yes, but on average, Nicholas, you will see very, very rarely those two phrases. Of course, you can see two phrases. If n is bigger than or equal to 6, you can see one phrase. On average, you will either see each situation, you will either see a phrase or you will not see the phrase. But the average, it could be even a fraction. The average could be less, could be 1/2 of a phrase or once, you know what I mean? The average is not always making sense in some sense, right? So yes, so it's just telling you how frequently you will, so you will say how many phrases on average you will see. Not in any given situation, you could say 2 phrases or 0 phrases, but if you only have a string of length 6, you would rarely see a phrase because 9 to the 6 is big enough number, right? All right, and now a question about the squirrel. Now, this question you could solve very rapidly if you understood my deer hunter example, right? Do you remember with probabilities? It's really it's really the same thing. That's okay. No need to be frustrated. Probability is very frustrating. That's all it is. But just be excited by the ideas. Don't worry about anything, right? That's how I think of it. All right, guys. So what was I saying? Remember the Russian roulette. So this is a kind of Russian roulette where there are 24 chambers and 4 of them are loaded. Same thing, right? Now with the Russian roulette, if you have one chamber loaded, how long will on average the game last until you hear the shot? So if you have 7 chambers loaded, if you have 7 chambers and 1 is loaded, on average, how many clicks of the pistol do you expect to hear? Very good. You expect to hear 7 clicks of the pistol, yes? So here, how long until you hear the first click of the pistol? So you can see it's the opposite of the probability. So it's 4/24 is the probability that you will hear the first shot. So it's 24/4. So first is 24/4 plus, once the first was shot, the second shot, we now have 24 chambers and only 3 loaded. So that would be 24 divided by 3. And the next would be 24 divided by 2 until you get 24 divided by 1. You understand? We have the 4 shots. And altogether, you get 50 shots, right? So on average, it will be 50 squares. The square will be digging until it finds all the nuts. You can solve it easily. Obviously, you can do infinite series, yes. But I mean, if you understood the import of doing the series once, then of course, you can just do it very easily. Yes, well, no need. You see, I mean, if you always try to make difficult things. Well, I don't always try to do that. I'm sorry, but you try to do difficult things easy, right? So if you understand, you calculated it already for the pistol, for the Russian roulette game, correct? You calculate and you already have intuition, right? You know that on average it's 7 games. You verify that your intuition isn't wrong. Why would you want to do the calculation all the time, right? You can figure out that it's always if you play a Russian roulette of you know, it's always until each shot, it's always 1 over the probability. That's how many on average shots you have. You understand? So that means for this game, it's 50. Good. Okay. And now, are you ready for the drums? The hard part. Now is the hard part. Why not? Why is it surprising? I mean, the squirrel is stupid. It just digs in the same boxes again, right? So the squirrel is not remembering anything. So the squirrel jumps around, just randomly digs. So the squirrel is digging here, then just for whichever reason it will be digging here, then for whichever reason next digs there. So maybe it's not. Maybe it's even. I don't know if it's surprising or not. Maybe it's even too small. I would imagine it will take longer, especially to the end. But it takes 50. I mean, actually, I don't know. I would imagine, because I know the Russian roulette thing, you know, so I would imagine it's 50 because, you know, it's 1 over the probability. So it's going to be 24 divided by 4 until the very first nut is found. Then now it's reduced to Russian the Russian roulette with 3 chambers loaded, where you have 24 chambers in total, right? So you now have a different probability. Yes, the squirrel can go back and dig. It doesn't remember anything, right? That's what it says. Having visited one sector, it can just randomly go to any other sector and just dig again. It doesn't remember which it dig, which sectors were dug, and which, you know. Yes, that someone knows that those squirrels remember that there are 4 nuts, but yes. What can I say, right? That's okay. The real squirrels, I mean, it should be grateful it's not a real squirrel. Real squirrels is worse, I'm not sure, or easier, right? They just probably remember where they buried the nut. Like, they probably remember hundreds of places where they buried them, and sometimes they do forget. All right, so let's first do question 12, right? First question 12 for Hanukkah. Now, guys, what do you think? I wonder, that's very interesting for me. What was your intuition? Did you have an intuition? Is one game better than another? Write your intuition, please, or tell me about it. Okay, so Steven says it's the same, and Gustavo says, and then Andrew says game 2 is slightly longer. And so I see it's kind of distributed. Some say game 2, some say game 1. So game 1 says great miracle, game 2 is miracle. Yes. Now let's look at it naively. So what's the probability of getting a great miracle? First spin to get great, it's 1/4. Second spin is also 1/4. So the probability of getting great miracle is 1 out of 16. The probability of getting miracle is the same, 1/4 times 1/4. Yes. So does it mean that there is no difference between choosing those games? Well, just for you guys to surprise you, I also programmed the simulation. Yes. Let me open it up. Yes, and thanks to Barry, I now remember to make this, if I can get it. Yes. Okay, so here is the
Mathematica.
Sorry?
I thought you hated Mathematica.
I do, but for you, I spent, you know, I'm such a lousy programmer. This code, it took me a while to do, even though I had it in my head, and then I realized this thing was or, and I was using and, you know. But here is the simulation. This means great miracle. You see, This is the great miracle. And let's see if I activate it, how many rounds it takes. Let's say here you got $9, right? Here you got $10. Here you got just $2, $4, $6, $11, $3, $33, $6, $22, $10, right? And what about miracle? Let's see what happens. $2, $3, $63, no, $8, $23, $3, $54. You see, it's distributed. Now, what happens if I play, let's say, let's look at the miracle, right? This is miracle, and here I am simultaneously playing, 10 to the power of 5, 100,000 games. Yes, we're going to play 100,000 games, miracle, and we're going to average. Sum is all the money you got for each game, and I divide it by all the games to estimate the theoretical average, right? What am I going to get a sense for this? Oh, I got this time I got 20.9. So basically there's a 0. And then what about again? And here I got 9 and 7, and let's do it again. Where is it doing something? Oh, you say it changed, right? 19 point, right? But essentially, let's do it one more time. Well, about $20. Do you see that it's about $20? Yes. What about a great miracle? Let's play this game. 16. 16.1 here. Let's play it again. 16.03 again. You see, you can see by this program, there is a difference between those games. They are not the same, Stephen, right? Now, why are they not the same? I mean, isn't it, miracle, the probability of that is one quarter times 1 quarter, great miracle 1 quarter times 1 quarter. Why are they not the same? Any ideas? Well, let me tell you. Think about it this way, guys, right? So you're spinning the statistics. No, I mean, I first knew the answer. I mean, that's, by the way, how I knew that my program is correct, because I calculated the answer, right? Otherwise, initially it was giving me some stupid things. So here. Think about this game this way, guys. If you are worried that the game is about to stop, yes? Let's consider great miracle first, right? Great miracle. So let's say I am at great, right? If I am at great, there is a chance the game will be stopped on the next round, right? The probability it will be stopped on the next round is what? Is 1 quarter that it would be great again, and then you're again in the parallel situation, right? And 1 quarter it will be stopped, and 2 quarters that it will be restarted. You agree? So you have 2 quarters chance that you will get neither great nor miracle, and it's restarted. 2 quarters. Probability 1/2 that the game gets restarted once you're in the parallel situation of the game being over. You understand? Now, suppose you're with miracle. With miracle, you're at miracle, right? If the next is miracle, the game is over, and you don't get as much money as you would if it continues, correct? So you're at miracle. Probability 1 quarter, you get miracle and the game is over. Probability 3 quarters that the game restarts. Do you understand? There is a 3 quarter probability that the game restarts. Whereas if you see, it becomes noticeable that there is a difference once you are about to reach the stopping point, once you're in parallel situation, 1 round before it could end. Because it always ends in the first game, great miracle, and the second game, miracle. You follow? So in the great miracle, you have 1 quarter probability. Once you're at great, 1 quarter probability that the game stops. 1 quarter probability the game is again in parallel situation. Again, you get great. And 1/2 probability the game restarts. And in miracle, it's either one quarter it stops, or you are 3/4 that you are not in a parallel situation and the game restarts. So the 3/4 make the difference. They are not the same at all. Yes, because the bigger payoff is that the other game, Miracle, has a much better chance of restarting once you get to the parallel situation. So it's a better game. So game 2 is better precisely, right? Now, how do you calculate the expected value? How do I know it's 20 and 16? No, I mean, you should be, on the other hand, you should only be much more excited. I mean, there's nothing to be said. We're surprised, and surprise is the stuff of existence. Yes, if you're surprised, if you learn something, then you should be happy about it. It means that you will be better and smarter, and that's what we want to do, right? All right, so I can teach you that entire thing. I mean, but let's see. So how do you calculate the expected value? I actually imagine the table, right? I imagine a huge table with many games, right? And some games begin with great, and others do not begin with great. So for game 1, Great Miracle, for instance. No, you improve at it. It's nonsense. So I just improve at it. I am not naturally good at this at all. I just figure ways around things. So here is what I observe, guys. So let's say we look at Great Miracle. Great Miracle. So E is the expected value, right? Now it's an average of sorts. Now imagine you're seeing a table. Can you see the table? And you're seeing many games played, right? So how many of those games begin with the word great? Right? You see basically the outcomes on those letters. So how many of them begin with the word great? 1/4 of the games begin with the word great. So I'll say Q are all the average of all the games that begin with the word great. Make sense? And the other part that makes the average are the games that do not begin with the word great, and there are 3/4 of those. You agree? 3/4 of the games do not begin with the word great. And what's the average there? The average there is the same as the average E, but +1, because if they did not begin with the word great, it's like you're starting from scratch, right? So the average for them is E +1. Do you agree? So I have this system of equations I'm setting up. So I do not know what is Q and I do not know what is E. Q is just the games that begin with the word great. So you understand, right? Now, what about Q? If I just look at the games in Q to calculate that average, I know that 1/4 of those have the second word is miracle, right? 1/4 of them have the second word is miracle, and that means those strings are of length 2. Plus, what about this one? Then the other possibility is 1/4 that the second word is again great. So I see great, right? If it's great, it is 1/4 here. And it is the same as Q +1, because it's the average. The average would be the same as the average Q, but I have the extra great, right? So it's like that's why it's Q +1. And the other possibility, and that's 2/4. 2/4, it is just the second word is neither miracle nor great, and that means we restarted. So there are 2 words plus the average is E, so it's E +2. That's how I figured it out. And then I solve the system of equations. It's not too hard to solve the system of equations, yes. And what do I get? I get that E is equal to 16. Just check it and see that E is equal to 16. Yes. I hope I don't need to explain this part. It's just technical, right? Just once the difficulty is setting it up. Difficulty is setting this question up, and you understand what I imagine. The reason I could solve this is because I could imagine the table. I imagine actual games. I imagine I have a list of games, and like a huge many times I played it, and I have like I actually imagine running this millions of times, like I did over there with the computer. And I imagine I see the writings, and I just group together the table based on things that begin with grade and average those, and then add to it the average of things that don't begin with grade. You understand? And then I just see that the answer is 16. Good. And if I do may I erase this and do the analysis for miracle. So now miracle. Actually, the analysis for miracle is slightly easier. Again, miracle, I have E, the average in total. 1/4 of those begin with miracle. So Q now represents things that begin with miracle. Plus 3/4 that do not begin with miracle, and the average will be E plus 1. You see why the average is E plus 1? Because it's the same after the first word. It's like this, the same probabilities that started. It's E plus 1. And what about Q? Q, there is 1/4 chance that second word. That's Q is first word is miracle. 1/4 chance that second word is also miracle, and then those strings are of length 2. Plus. So with this game, it's either game stops or completely restarts. Great miracle, it could stop or be in the perilous situation again or restart, right? So there are 3 possibilities. Here there are only 2. That's the difference. Top equation the same. Bottom equation is different. Bottom equation is what? It's 3/4 restart. And then you get E equal to 20 once you calculate. Good. You can trick your friends with this question, wonder what they would say. Although I noticed some people see that the game is not the same. Others, I really enjoy when people think the game is identical. How many of you got this question correct? Well, okay, we'll see. All right. Now, for the last question, are you still able to function, guys? Are you okay? I thought it will take less time, but apparently going over the exam is hard enough. Right, so this is actually a famous question. You know who thought of this question? Feynman. Richard Feynman. You should read his book. He was an interesting physicist. And the solution here is, of course, much more complicated. Do you want me to go over the solution? I think I actually came up with a better answer before, but now I don't remember it. And I wrote another one, and it's kind of like this, 2 pages. Should I go over it, or you had enough? Okay, I'm glad you see, guys. I hope I'm not holding you too much. If you are tired, and it's I hate emails. You know, I mean, I can email you my thing, but I don't think you will be able to read it. I wrote it for myself. Right. So if you really have to go or tired, by all means, you leave. But I hope you're interested in those questions. That's pretty much what drives me. I don't care about grades or anything else. I never did. I just like this subject, and I hope you are the same. All right, guys. So there is an interesting. First, you need an interesting idea about probability. that you have conditional expectation. And you can actually come up with this idea on your own. I mean, when I had to solve those questions, I realized how to do that, because just let me try to explain, hopefully I'll succeed, is this thing. Imagine that that you have, here is your values of x. Let's say this would be the value of x. And this is the probability. So we have, let's say, probability P1, probability P2, probability P3, P4, P5, and onwards, right? And here I have, let's say, X1, X2, X3, X4, X5, right? Let's say just X5. Those are the different values, right? And I want to calculate expected value here, right? So I can, in some sense, I can use a conditional probability, because I can, let's say, I can group those two values together, and if it's useful for me, and I can group those values together if I like, right? In other words, I see it's a table. When you realize that calculating expected values like using a table, then you realize you can produce all sorts of groupings. Yes. Now, what is that useful for me? So look at it. If the expected value of x is simply x1 times p1 plus x2 times p2 plus x3 times p3 plus x4 times p4 plus x5 times p5. Yes. And you remember how I grouped them. I said I'm going to look at this together, and I'm going to look at this together. Yes. Now, what I mean, look at it together. I can, I can consider this events. So let's say this is, let's say, the event A. So this is the event A, right? And this is the event B, right? I want to condition the expectation based on A and B. Make sense? So that's why, so what can I do here? Look at it. I can make it a conditional probability by dividing and multiplying by PA, right? So what I can do here is I can say this is X1, P1 divided by probability A plus X2, P2 divided by probability A, all of it PA, yes? Plus, same thing here. I can say it's, well, same thing here. So, you know, I can divide by PB, right? This is just the same thing, but the factor is PB. Same idea, right? What does it give us? It gives us, this expression is conditional expectation. This means X given that A occurred, right? So this is the expected value of X given that A occurred, times probability of A, plus this would be the expected value of X given that B occurred, times the probability B. This is conditional expectation, which I didn't teach you in class, but it's something that if you understand the tables, you come up on your own, just like we did. The same idea actually works for the Dreidel example. This is what was happening, you see? I condition on what happens. And you can see that this looks exactly like the Bayesian formula, but it's the Bayesian formula for the expected values. And I do not know if it was necessary for the Feynman question, but that's how I solved it, right? I think I solved it an easier way, but I forgot my solution and then I solved it again. And it seemed slightly harder than what I had initially in mind, but maybe I don't remember, right? So are you ready now for the suffering, or you want to take a deep breath? Maybe it's my suffering because I have to write it. So here is how I analyze it, right? So why do I need this idea? Is because I need to know the expected value is easiest to answer if I know what was the tastiest dish that a person ate. See, so you are going to have n dishes, and out of the n dishes you choose for the exploratory phase, you choose k dishes, correct? So this is what I condition based on the best dish. So I know that the expected value is summation, where j is k. Then j is the tastiest dish among the ones that I was able to sample, to n. The expected value of x given j plus, and I will explain to you what it means, m minus k plus 1 j over times pj. So this is my conditional expectation, okay? And I kind of wrote it like this. Let me try to explain what I mean. So I want to know, let's say, if you're sampling k dishes, what you're going to do? You sample k dishes. One of them is going to be the tastiest. So what's the tastiest dish you have? Maybe it's k. Maybe it's k plus 1. Maybe it's k plus 2. Right? If you had k, at least k plus, you would have k plus 1 dish. Sorry, k dish or k plus 1 dish or k plus 2 dish, or maybe the nth dish, right? And what you do is this part is your exploratory phase. It's where you select a dish at random, and then once you selected your favorite dish, given that you selected this is your best dish, you're going to repeat it for all the trials. So you have m minus k trials that you eat the same thing, right? At the end, once you already sampled k trials, m minus k trials, you're eating the same thing. And I just took out that one dish that you selected. You see that best dish that you selected, plus 1. So that has the payoff j. So this is how much you get for j, and for the other k minus 1 dishes, you ate different things. Does it make sense? You ate entirely different things for those k minus 1 dishes. Are you still following me, guys? It's very difficult, and it's very difficult to communicate. Not so difficult to actually calculate once you get the idea, but difficult to explain. So now I want to calculate this part. What is the expected value of x given j? Now, what do I get there? The expected value of x given j. This I can break again, which dishes I got where. So I imagine I have k minus 1 variables. K minus 1 variables, because you understand, this is the summation. This is the summation of the sample dishes, except for the favorite dish among the sample. You follow what I'm saying? So it's something like maybe it's you got dish 1, dish 2, dish 3, dish 4, all the way to dish k minus 1, and then dish k, and dish k was added into this batch. Yes. So how this you also condition which of those I can do another conditioning here. Which of those dishes was the one that was favorite, the one that was favorite, and there are k possibilities for the sample that produced the favorite dish. So it's k times. Now once I know the k, the other random variables are, if I know I fix j, the other random variables can produce values from 1 to j minus 1. So that means there are k minus 1 additional values, and this for each individual random variable, the summation is t equal 1 to j minus 1 t over j minus 1. And the entire thing I have to multiply by 1 over k. Do you follow? Or did I lose all of you? Then yes, this is the hard part. Do you understand what was my thinking? Yes. So I actually did not write it explicitly, but I conditioned this expectation yet again. You see, what do we have, right? So this means this part here, are the K dishes that I randomly sampled, right? The K-1 dishes, because I already borrowed the best dishes already. The best dish is J, and it's already here. So they are K-1 summations, right? Now, first thing I need to ascertain is which of the sampling trials produce J, the best tasting dish, right? So it could be first sample, second sample, third sample, fourth. So that's why there you see the K here. The K is for first, second, third. There are K possibilities. Yes, right. The 1 over K that cancels it. This one is the probability that it was sample number 1. It's 1 over K. Probability it was sample number 2. It's also 1 over K. So all of them are actually 1 over K. There, each of those trials were equally likely to produce the best tasting dish. Do you follow? Now, once I know that, I see that you see there are K-1 variables that produced the less tasty dishes, and each random variable is then equally likely to produce either dish 1 or dish 2 or dish 3 all the way to J-1 dish, because they cannot exceed J. J is the limit. They are limited by J. Yes. So the K-1 here is for the summation of K-1 trials. Yes. So I conditioned based on which dish, you see. So that's so there are K possibilities. It's dish 1 or dish 2, etc. They are identical, so I can just multiply it by K. So sort of summing it, like it's the same summation for whether it's dish 1. You have summation for the remaining K-1. If it's dish 2, you have summation for the remaining K-1. They're all symmetric or identical. So that's what you get. Yes. And then let's simplify it further. If you simplify this expression further, you get simply that this is the K is cancelled. So this is K-1, and summing up the T's from 1 to J-1 is the same as J. Now you have lots of combinatorics here. J choose 2 divided by J-1. That's what it simplifies to. Do you see? Because 1 plus 2 plus 3 plus J-1, it's like I have a younger brother. Remember that? I have a younger brother and you don't know what's my age. So that means my age is at most J. So you choose J, choose 2. The oldest age is for me, and the other age is for my brother. And when you simplify this expression, what you get is K-1 divided by 2 multiplied by J. So that was the hardest part so far for the calculation. I hope you understood it. If you have any questions, please let me know. Good. Next is I want to estimate PJ. What's the probability of J being the tastiest dish? Now, if J is the tastiest dish, it means that I selected K-1 dishes that are less tasty than K. It means, let me see. So PJ, it means that the probability is J-1 choose K-1 divided by N choose K. This is the probability that J is the tastiest dish I selected. It means that additionally to the tastiest J I selected, selected the remaining K-1 to be lower. Yes, that's what I get. So what does it make my summation? And the summation is, if you distribute it, it's just the previous thing. I just put everything together, right, from here. The summation is Yes. So this you can simplify further. You see, I can factor here everything. Look at this equation. I can factor everything outside that it is not involving summation of j. So that becomes k minus 1 divided by 2 plus m minus k plus 1. Right, this thing times the and also divided by n choose k times the summation j equal to k all the way to n of j minus 1, k minus 1. Are you with me? It's now algebra. You see, you see this j minus 1. I just factor this thing out. I factor everything that is not involving j to make it simpler for me, and this is what I see. Now, do you recognize the summation? That's another combinatorial identity. You see this j times j minus 1. It's like that committee thing. Remember from discussions and examples. It's like the committee thing. So we have a leader and we have followers. Right, so one of from 1 to j individuals is selected to be a leader, and k minus 1 followers are adjoined, and that's the same as I can just rewrite it. And say this is the same as summation k j choose k. Agreed? Same as first choose the committee and then choose the leader. So what you now have is that this is now the same as and then what's more? What is the summation? We're almost done with this question, guys. This is the hardest one. What is the summation? If I sum from k to n, j choose k, then what is that equal to? Nicholas, Camille, what is this identity? What is that equal to? Remove the summation. Summation of j choose k, where k goes from 1 to n. What is that equal to? Well, it equals to n plus 1 choose k plus 1. So it's n plus 1 choose k plus 1. Do you see why? Because if you choose k plus 1 individuals out of n plus 1, then you can condition on the oldest individual, let's say, right? And maybe it's individual k plus 1, or it's the individual k plus 2, or all the way to n plus 1, and adjoin the other k individuals. So it's this divided by this number by n choose k times k minus 1, this is the k here, k minus 1 over 2 times k plus m minus k plus 1k. Okay, I reduced it already to a nice form. Now this can still be simplified. What is this number here? You can either use algebra or you can use another identity. It's also combinatorics there, right? So this is the same as n plus 1 divided by k plus 1. Same thing, right? N plus 1 divided by k plus 1. Nice, right? And what we have is now we are left with the following function. You see this 2, I can factor it. I can see that this expression is equal to n plus 1 divided by 2k plus 1 times this expression, times 2m plus 1 k minus k squared. Yes, this is what it ends up to be. And now to figure out when is this function optimized, when it's biggest, I don't need the constants. I just need this function. I can define f of k to be equal to 2m plus 1 times k minus k squared divided by k plus 1. And this function, just take the derivative, set it equal to 0, solve, and you will get that k that maximizes this quantity is 2m plus 2 minus 1. So it's the integer closest to this. Yes? So now you know you can use this formula when you go to a restaurant. Congratulations. Well, thank you for waiting. I hope you understood something from it. I hope you will try this question again and enjoy, and continue studying statistics and probability and be smart. And don't worry too much over grade. As I mentioned, I have to, because it's in a take-home exam, it's very hard to tell apart anyone, but from good students, from bad students, I push it a bit higher, and I keep you in safety. In other words, you know, right? It's mostly, hopefully you enjoyed those questions. Hopefully you will think about it again. Well, guys, if you don't have any more questions, goodbye forever, maybe.
Bye, Professor.
Bye.
Thank
you very much, Professor.